Hello students, so today we will be learning stereochemistry, in which we will discuss the topic optical activity, polarization, chirality. Okay, so we know light is electromagnetic wave, so it will have oscillating electric and magnetic field. Okay, so light from sun, incandescent bulb, all these are unpolarized light. So what is unpolarized light? Unpolarized light, it will have electric field vectors in all directions perpendicular to direction of propagation. So here you can see an unpolarized light, it has electric field vectors in all direction perpendicular to direction of propagation. Okay, whereas polarized light, it will have electric field vector in only one particular direction perpendicular to direction of propagation. Okay, so to describe this polarization, you need to know this process. Okay, so consider a light source. Okay, so from this light source you get unpolarized light. See, I told you electric field in unpolarized light will have electric field vectors in all directions perpendicular to direction of propagation. That is what I showed it through arrow marks. It has electric field vectors in all directions. Okay, when it passes through a polarizer, you get a polarized light. Polarized light is basically electric field vector in only one particular direction, okay, which is perpendicular to direction of propagation. So what does this polarizer do? Basically it is an optical filter. So it will optical filter, basically it blocks vibrations from other directions and it allows only one particular vibration only one particular direction to pass through. So basically polarizer is an optical filter which blocks vibrations in other directions and allows only one particular like vibration to pass through it. Okay, so that is a polarizer. So now you get polarized light. So and when you pass this polarized light through an optical active sample, what happens is it will this optical active sample will rotate the plane of polarized light. Okay, so plane of polarized light towards left or right depending on the optical active sample. Actually, what is optical activity? You need to know before that what is optical activity. Basically, it is the optical activity. Basically, optical activity, it is a property of a compound to rotate the plane of polarized light. See here, the plane of polarized light. So it is rotating the plane of polarized light. Okay, so that is what is optical activity. The property of a compound to rotate the plane of polarized light. That is optical activity. And the molecules which exhibit this property, you call them as optical active compounds. Okay, so that's it. And so now in this beaker, if you like place an optical active sample, what does it do? It will rotate the plane of polarized light, okay, towards left or towards right. So if it rotates the plane of polarized light towards left or to the anti-clockwise direction, towards left or towards anti-clockwise direction, you call them as levorotatory. So basically it is an L isomer, or you represent with minus. Okay, so and you call the compound as dextrorotatory if the optically active sample rotates the plane of polarized light towards right or clockwise direction, then you call it as dextrorotatory. So that sample will be a D isomer. Okay, D isomer, or you represent it as plus. Okay, so so now I have discussed what is optical activity, polarized light, unpolarized light, and dextro and levorotatory. Now what are optical isomers? Optical isomers are basically compounds which are non-superimposable mirror images of each other. So before that, I'll tell you what is chiral. Chirality, this chirality. Chirality is basically the property. See, optical activity is also property. So, and what are chiral molecules? Chiral molecules, they are basically molecules which are non-superimposable, which has a non-superimposable mirror image. You call them as chiral molecule. So if a molecule has a non-superimposable mirror image, you call them as chiral molecule. Okay. So that property is what is chirality. Okay, and what is meant by non-superimposable mirror image? Okay, non-superimposable mirror image, if you consider this as compound A, okay, and this, and if the mirror image is this, okay, so compound A's mirror image is this, and if I place my right hand towards left, here you can see, if I place this over this, it forms a non-superimposable mirror image. So if this is a compound and if this is a mirror image, if I place it over this, you get a non-superimposable mirror image. It is not superimposable, right? So that is what I said. If it has a non-superimposable mirror image, you call the molecule as chiral, okay, and the property is chirality. And if the molecule is chiral, it will be exhibiting optical activity. So chiral molecules will be optical active, whereas if the molecule has a mirror image but it is not superimposed, but if you can superimpose that mirror image, then it is a chiral molecule. Okay, So basically the mirror image is superimposable, then it is achiral, and so it is optically inactive. Okay, now this is one example. See, in this compound you can see this is a compound. This is a Fisher projection. You can represent it using wedge, flying wedge, or using Fisher projection. So this is a Fisher projection of the compound. So here you can see this is a compound. Okay, and here the mirror image, I have drawn the mirror image over the right. Okay, now you can if you superimpose this over this, you can see that it doesn't superimpose, it forms a non-superimposable mirror image. So basically these both are enantiomers. So here the mirror images are non-superimposable, so you call them as so they are chiral, so they are enantiomers. Okay, next we'll discuss so I have discussed what so basically optical isomers is basically compounds which has a non-superimposable mirror image. Basically optical isomers are two compounds which have non-superimposable mirror images. Okay, then we'll move into asymmetric atom. Okay, asymmetric atom is basically an atom which has four different atoms or groups attached to it. So if you consider this is a carbon atom, it has four different atoms attached to it. Okay, four different. Here one is CH3, the other is Cl, and the next is OH, and then H. So to this carbon atom, four different atoms or four different groups are attached. So you call them as asymmetric atom. This is an asymmetric atom. And if there is only one asymmetric center, here this is the asymmetric center. Okay, if there is only one asymmetric center, then that molecule will be optically active, that molecule will be chiral. If a molecule is chiral, automatically that molecule will be optically active. Okay, so since it has only one asymmetric center, you can say that this is chiral, so it shows optical activity. Okay, it shows optical activity means it can rotate the plane of polarized light. Okay, so and then consider this molecule. Here you can see there are two asymmetric centers. Here this carbon is attached to COH, then OH, then H, then to CH, OH, COH. Okay, so this is an asymmetric center and this is also an asymmetric center. Basically it has two asymmetric centers. And if you draw the mirror image of this compound, see, basically if you looked into this, you feel like it is non-superimposable, but actually is it optically active? No, it's not optically active. It has two asymmetric centers. Okay, why is it not optically active? The reason is it has a plane of symmetry. See, if you pass a plane of symmetry over here, you have a plane of symmetry. So because of this symmetry, it is not optically active. Okay, so actually since it has a plane of symmetry, it is not optically active, so it is a chiral. Okay, this is a chiral. Okay, and the other one more example. Here you have this compound. Okay, is this optically active? So here there is center of symmetry. Here you can see from this point, if you move towards the top, you see a CH3, and to the bottom if you move, you get a CH3. Again from this position, if you move diagonally to the side, you get a COH, and below if you move, you get a COH. So basically this is a center of symmetry. So compounds which has a center of symmetry, you represent it as I. Okay, basically if it has a center of symmetry or if it has a plane of symmetry, what happens? They are not optically active. Okay, so they are a chiral. Basically if you have a center of symmetry or plane of symmetry, then it will be a chiral. So if it is a chiral, it will be optically inactive. Okay, so even though this has asymmetric centers, it is not optically active. It is a chiral. Okay, next, I hope this much is clear, and then we'll move to enantiomers. Enantiomers are basically stereoisomers. Enantiomers are basically stereoisomers related as non-superimposable mirror images. So here I said these are both mirror images, non-superimposable mirror images. So these both are enantiomers. Okay. So when the compounds are related as non-superimposable mirror image, then they are enantiomers. Okay. So this A and B are, we call this A and B as enantiomers. Okay. Next, moving on to racemic mixture. Racemic mixture, it is basically 50-50 proportion of D and L isomer. See, enantiomers, I told you, like there will be a D isomer and there will be an L isomer based on whether it is rotating towards right or left. Okay. So if for a particular compound, if a compound has a D isomer, the compound will be having an L isomer, right? Its mirror image will be an L isomer. So if these two compounds are in 50-50 proportion, then what happens? Basically the rotation due to one compound will be cancelled by the other compound. Okay. So in this case, what you can see, it is a DL. If suppose I am having a D isomer, okay, and if it is rotating 50 degree, and again I have an L isomer, so it will be rotating 50 degree towards left. So basically the rotation is getting cancelled. So what happens? Net effect, there will be no rotation. Okay, so there will be so this racemic mixture will be optically inactive. Okay, racemic mixture will be optically inactive. The reason is it will have 50-50 like proportion. 50% of D isomer, 50% of L isomer. So rotation due to one isomer will be cancelled by the rotation of the other isomer. So net effect there won't be rotation. So such compound, basically that racemic mixture will be optically inactive. Okay, and the process by which an enantiomer is converted to racemic mixture, it is called racemization. Basically enantiomer, if you consider as a D isomer, if you consider D isomer and you convert it into D plus D and L isomer. Okay, so this is an enantiomer, okay, and this is a racemic mixture. So the process by which you convert an enantiomer to a racemic mixture, you call it as racemization. Okay, then you have retention. Retention is basically when the configuration is retained. Okay, when we see configuration is retained, you might have studied of R and S configuration. Okay. If the R configuration remains R after reaction, if the compound was having an R configuration, and after the reaction, if it changed to, if it didn't change, like if the R configuration remained as R, then you call this retention of configuration. Okay, basically SN1 we studied, there will be retention of configuration, right? Whereas if the R configuration changes to S, then you say there is inversion of configuration. Or if a compound initially it was S, okay, then again after the reaction changed to R, then there is inversion of configuration. Okay, so to explain this in detail, for example, this is a compound. You can see there are four. This is an asymmetric carbon, right? So to it, 4 different atoms are attached to it. So here you can see this is a flying wedge model. Like CH3 and OH, it is in this plane of this board, and then Cl is protruding out, and H is behind the wall. Okay, so this is the structure. So in this structure, for giving this RNS configuration, it is just to make you understand. Okay, so how do you name in RNS configuration? To determine RNS configuration, basically you need to give the priority, like 1, 2, 3. You just number them. So you give the priority based on atomic number. So the atom which has great atomic number, great atomic mass, it will be given higher priority. So in this case, you know, Cl has a higher atomic number, so it is given priority 1, and OH, oxygen, has again higher atomic number compared to the other groups. So you give the priority as 2, then CH3. Okay, so you number it as 1, 2 and 3. Okay, and hydrogen has 4. So again you move from 1 to 3. When you move from 1 to 3, you know it is an anti-clockwise. You are moving anti-clockwise. So when you move anti-clockwise, you represent it as S. So it is having S configuration. So remember, while naming this, lower priority, the atom or group which is having the lower priority, basically which you have numbered it as 4, it should be in the dash. Only then you can give it as anti-clockwise. Okay. So basically you are looking only at rotation of 1, 2 and 3. Okay. So when you move from 1 to 3, it is S configuration. Okay. So provided you need to say that 4th priority group is in the dash position. Okay. Again, there is the same compound written in a different way. So you can see here chlorine 1, OH 2nd priority, CH 3rd priority, and here you move from 1, 2, 3, 1, 2, 3 this direction. So it is clockwise. When it is clockwise, you assign it as R configuration. So basically, a compound, if this was a compound and after reaction or something, if the configuration after it changed to R, then you say that there's inversion of configuration. So earlier it was S, then changed to R. Okay, so this is basically inversion. These two have inversion of configuration. Okay, again look at this here, 1 2 3, here it is S. Okay, this S basically if a compound was initially in this, after reaction it maintains this S configuration, that means retention has taken place. So here when you compare these two, we can see that this bond, CH bond, this is constant, right? But the other two, the other three bonds changed. So basically this is just a rotation among the molecule is actually identical. All what happened was just a rotation. Okay, so that is why this and this component is the same. So you call retention of configuration. Whereas in the other case it was inversion. When you compare this with this, you can say A, this is B, and this is C. So when you compare A and B, there is inversion of configuration. Whereas when you compare A and C, there is retention of configuration. A and C, you see retention of configuration. So that's it. I hope this stereochemistry is clear to you. That's it. Thank you.